let's look directly at, we looked at chapter 12, the rigid body, and we have a thing called dynamics wrap-up, and I'm listing it as the final. It covers F is equal to MA. It covers, that's what that is too. It covers energy or power. And this is energy. And impact. And I think, yep, that's it. So this is the whole thing. So what I'm going to do, go back to Blackboard, go to the very top, take you here. It launches a new or a tab, and I'm trying to make it go down. Okay, so you go down to Dynamics. What you're going to find is I went straight, I don't think it's in here, I went straight to this one and got the problems from here. I went straight to this one. I didn't take those first two, but I took that one and that one. And then I took impulse. There are some better problems here. The first two were not that good. This one was okay. I really liked the 10-4, but it may have been too much under our circumstances at this point, and that's pretty much it. So you can go in here and watch some of these videos. He has some video lectures. He has some worked problems. I would say go and look at those. And he has the video of the work problem and a PDF solution there of the worked problem. And in a PDF solution, you can see he took the problem and worked his way through it. Those launch on their own pages. If we go back, he has two-dimensional X and Y. He has normal and tangential, although I'm not asking anything there, but he has those. And he has the polar coordinates. So he has the full allotment here. He has the acceleration, the two accelerations. In the energy, he has the introduction to it. And he has conservation of energy. So these are good videos to watch. Power and efficiency, which this is a good problem here. And for a system of particles, for example, something like that, this A and B would be considered two particles, but they're boxes. The tension is common between them as long as this pulley doesn't have any frictions. And he works the problem here, so that's a pretty good problem. This is a pretty good problem here, which I'm not quite sure how he's got. Hang on. I think I just clicked that. He works his way through the whole thing. part is impulse. So he's got impulse for a particle. So I would say read all of that and watch the videos. Okay, I lost track. Okay. Okay, coefficient of restitution. I would say watch this one definitely. And here's a problem similar to the one you have. Here's a problem almost exactly like the one you have. So I would say definitely go in, look at his solution here, which actually appears to only be one page. And if I go to coefficient restitution, one-dimensional particle collisions are one-dimensional, meaning the velocity is straight along the plane of impact, and he'll talk about this. And then the second one is where they are not. In other words, the balls come in, the blue vectors come in, they hit each other, and then they bounce and continue along the blue path. He is labeling the plane of impact. The red, or the N here, labels the line of impact. And so he has a couple of problems here. Here's one where he's got two balls going to impact but off at an angle. He's determined that that impact angle is 30 degrees, and he works his way through the two problems. The one problem with the two pucks or balls or whatever. So go through those. That would be chapter 8, 9, and 10. Now let's look at our content and go back to it, and we're just going to look at this straight up, and I will start the problem for you over here on okay, on the OneNote. So what I'll do is I'll grab this. I'll just go over here. I'm just going to drop it. So what I'm going to do is I'm going to go ahead, make a free body diagram. Make sure I'm still going. I'm 8 minutes into this. Okay. So, alright, I don't know. So, we have a force, which is a normal force. We have a weight, which 50 times 9.81. We have this thing up at 20. We're assuming since we pull it this way, it's going to go that way. If it goes that way, you're going to have a force due to friction. He told us that the coefficient of friction is 0.3. If it is moving, Although he stated if the static coefficient of friction is 0.3, what is the rate of acceleration of the box? How far did the box move in 3-second period? He really should state that that's also the dynamic friction. What I mean by that is, let's say you had a dresser sat on a really soft carpet and then you were shoving it. Eventually you push it. Once it gets moving, your force required to move it goes up to a point, then it drops off when it releases. This is generally the static friction. This is generally the dynamic friction. So we're going to assume the static and the dynamic are the same. You've experienced this, but we're just going to go with that. All you do is the sum of the forces in the y equal mass times acceleration, the y. The block is not jumping off the ground or going through the ground, so therefore that's 0. Sum of the forces in the x, and it is moving to the right. You're pulling it, so it's going to move, unless you don't pull it hard enough. So from this, you're just going to have normal force being positive plus 200 sine of 20 minus 50 times 9.81. Sorry about that. But let's get back to our problem real quick. From this, I can find my normal force. I can take that, put it in here. So I'll actually have a number for this. And so the next thing I can do is this. Is I can basically go in and sum the forces in the x direction. If this is positive, then I have 200 cosine 20. And the only thing I have pulling it back is 0.3 times n, which I figured out from here. So I know this. Well, that's equal to the mass of this thing, which is 50 kilograms, times the acceleration of the x. If I have this, this will be a number which is constant. And, like the problem stated, what is the rate of acceleration and how far did the box move in 3 seconds? So I get a number here, and if I'm looking at the constant acceleration terms, I get this. The question is, how far did it move? Then essentially I can take here, I can take this term, move it over, take this term, take this term, move to that side of the diagram, put a minus, take all of this, now how far did it move? First of all, did it have an initial velocity? Okay, it's pulled across the surface. It didn't state whether it did. The only thing I can see is he said it was a static coefficient of friction, which means that possibly he's implying it's sitting dead still. And if it is, Then this term is 0. And all you get is how far did it move? AX times 3 seconds squared. I guess it was 3 seconds. You know that. That's how far it moved. I'll go ahead and stop the video and restart it on the second one. It's only 15-minute video so far, but that's fine.